And I want to thank all of you who have tuned in for this. We have not planned to make a formal presentation in the sense of going systematically through slides with an analysis of a particular topic. Instead, we plan to invite each other to comment and have a conversation about this interesting development that has been called GPT-3. Could you put up the first slide, please? So let me begin by setting a few parameters about what we're going to talk about. Now, the title of this presentation was Limitations for Curiosity and Discovery in OpenAI GPT-3. But I don't think we're going to have very much to say about curiosity or even discovery, unlike the very good talk that Nick just gave us. He was talking, of course, about a system that was specifically designed to model curiosity and engage in discovery. This doesn't really apply to the kind of model that is behind GPT-3. Now, GPT-3 has this letter 3 or number 3, indicating that it's the third in a line of systems that have been developed by OpenAI, each increasingly more powerful than the previous one. And I think it's safe to say that GPT-3 is a good example of the capabilities of deep learning based large language models for natural language processing. I suspect that in our discussion, we will be focusing on the strengths as well as the limitations of this particular system. And also, I think we will reflect on what this says about deep learning approaches more generally. If there's an opportunity, we may reflect on practical uses and challenges, and even what the future holds. But let me begin by showing something that may help everyone be on the same page with respect to what the excitement is about. So Jason, could you show the second slide, please? What I'm showing here is an excerpt from an article that appeared in The Guardian. The title of the article was, "A Robot Wrote This Entire Article. Are You Scared Yet, Human?" And the article begins, entirely written by GPT-3, I should say. "I am not a human. I am a robot, a thinking robot. I use only 0.12% of my cognitive capability. I am a micro robot in that respect. I know that my brain is not a feeling brain, but it is capable of making rational, logical decisions. I taught myself everything I know just by reading the internet. And now I can write this column. My brain is boiling with ideas. The mission for this op-ed is perfectly clear. I am to convince as many human beings as possible not to be afraid of me. Stephen Hawking has warned that AI could spell the end of the human race. I am here to convince you not to worry. Artificial intelligence will not destroy humans, believe me." Now, this sort of production is strikingly good. I think everyone would agree that it's logical and coherent, that it seems to be addressing a topic with some force and conviction. And I also think that when we see examples like this, it's very easy for us to lapse into what has been called the ELIZA effect. ELIZA being the name of a program developed by Joseph Weizenbaum in the late 1960s at MIT that imitated a Rajayan psychiatrist by searching for keywords in input statements from its users and then parroting back fairly stock phrases. It was sufficiently powerful that users quickly suspended all disbelief and engaged the system as though it were an intelligent, helpful interlocutor. And we see this effect, I think, whenever we are struck by the magic of complex systems that are performing in ways we hadn't expected. So beginning this discussion, we should certainly keep that in mind and remind ourselves that whenever we see a complex system in operation, we should always ask how we know it's doing what we think it's doing. In the case of language learned models like this, we normally evaluate the models on systematic tests of one kind or another. But again, these tests are somewhat arbitrary and not necessarily complete. And when we see that progress is made in some aspects of testing, we still have to ask what it really means. We are, after all, dealing with black boxes that can't be inspected and whose behavior is beyond our comprehension. Nevertheless, this kind of progress in natural language processing is truly interesting and remarkable. And I guess we can begin with the question of what's really going on. How is this sort of production possible? Let me, I can certainly continue to talk about that and offer my own thoughts and answers to that question, but let me ask either Peter or Ed to jump in and comment at this point.
Okay, I'll take the chance to jump in. So I agree with you with this idea that we can attribute too much intelligence to things that are kind of dressed up in nice clothing. You know, I think of it as the Chauncey Gardner effect in Being There, where if you're wearing a nice suit and you say some words that seem like they're on topic, we'll attribute great meaning to that. And so you have to be careful to evaluate these things more clearly. And you know, one way you could have done that is to say, let's not look at the one article that was published, but let's look at the 10 other ones that were discarded before it was published. So every time you see one of these, you know, you give it a prompt, it shoots back some text, and the first couple ones are no good, and then the fourth or fifth or 10th one is seems pretty good. And the human who's responsible chooses that one. So on that note, we can say, well, you know, we're only a quarter or a tenth of the way there. Then the other thing is, what about all these mistakes it's making? And why are they so different from the mistakes that, you know, students in writing an essay would make? And so that's a clue that is doing something that's very, very different from what humans are doing, and we should evaluate it that way. And it shouldn't be surprising that it's doing something different because it's learned in an entirely different way, right? So everything these systems have learned have been by feeding it in sentence after sentence, and it has a voracious memory. We're building models now with trillions of parameters, so it has the ability to memorize those. But we try to convince it not to just memorize, but rather to generalize. And the way we do that is by forcing it to guess. So you take a sentence, you feed it into the system, you block out one of the words in the sentence and say, what's your best guess for what that word should be? What word would make the most sense there? And in that way, the system learns to make some sense, but only in a very limited way, and not in a way of interaction with the world that a human would have. And so the output is confusing to us. I think there's an opportunity for us to do better. You know, in the previous talk, we heard about looking at different modalities, and we're kind of on the cusp now of being able to feed in images and video and audio as well as just text into these models. And if we can do that, then maybe we'll be one step closer towards having them have an understanding that's more like a human level of understanding. Let me stop there.
So maybe I can pick up from there and just say, this is a delightful topic to be talking about, since it is so exactly a great illustration of the promise and the challenge of AI. On the one hand, it looks fantastic. It looks like magic. It looks like AI is solved. And when you dig into it, you discover, oh my God, there's problems in there. And I don't quite know how to find those problems. I don't really know what to do about them. But I do have a residual fear that somebody's going to do something to exploit me. And so if you know how GPT-2 was announced by its spin doctors, right? The technologists announced the thing, and the spin doctors in the company in open mind got up there and said, oh, we're not going to make this thing available to anybody because it's going to produce misinformation and it's going to control the world. And I'm thinking, what do you mean? Putin is paying people, humans, to write misinformation. I'm not going to be fooled by a machine when there's so many better, more talented people doing this. What are you talking about? So you have to decouple the hype and the nonsense from the actual technology. And you have to look at the technology, and then you have to say, it is a marvelous achievement. And yet, as Peter and David both said, there are problems there. So I wonder, Elizabeth, if you could show the slide that I sent you, or would you like me to show it? Just one slide, or maybe two slides. It's a piece of text also produced by GPT-3, or GPT-2 actually. Yes, this one. This was a GPT-2 piece of text. Okay, so it's not the most wonderful example. But look what it says, right? So the humans, as Peter said, you give it a little bit of stuff. So you give it, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And now you switch on the machine and you have what is called a GPT jockey, as Peter said, right? You have this guy who knows just what kind of prompts to give it so that the thing produces something that isn't too crazy. Right now you get, after 10 tries, the scientist named the population after their distinctive horn over its unicorn. These 4-horned silver white unicorns were perfectly unknown to science. So now they have a distinctive horn, but they also have 4 horns. So can you explain what you mean, right? Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. 2 centuries from what? What mystery? What is solved? Dr. Jorge Perez, an evolutionary biologist from the University of La Paz, and several companions, now we have suddenly several people, were exploring the Andes Mountains when they found a small valley with no other animals or humans. No other animals or humans, right? Perez noticed that the valley had what appeared to be a natural fountain surrounded by 2 peaks of rock and silver snow. That's kind of a weird sentence, but okay. Perez and the others then ventured further into the valley. By the time we reached the top of one peak, so are you in the valley or on the peak, right? The water looked blue with some crystals on top. We assume it's the fountain, right? So Perez and his friends were astonished to see the unicorn herd. These creatures could be seen from the air without having to move too much to see them. They were so close they could touch their horns. Now remember, we're on the top of a mountain and these things are in the valley. We can see them from the air, but we can touch, so close we can touch the horn. This means either there's complete nonsense here or there's a very long horn on this unicorn, right? And so on. So when you look in more detail at the internal logic of little pieces of this, and you go back more than 2 sentences, you discover there's just no consistency. What happens is the way this thing works is it has a very large memory of little fragments, little sort of not quite sentences. Let's say for arbitrary, let's say 50-word fragments or 12-word fragments. Imagine you built a machine to read all the texts in the web, and you made a big Excel spreadsheet that was 12 columns long, and each word was in a different column. You just made one that was billions and billions of lines long. So if you take a sentence and you end with some words, you go and look in the spreadsheet and you find other sentences that begin with those same words, and you just put them on top, and you just keep tiling, you just keep going on to the right. You just keep adding more and more sentences, and you have like 15 or 20 possible extensions, and you pick one that seems to be good because it fits previous words you've used, and you sort of muddle your way through that. That's essentially what this thing is doing. So it is surprising on one hand that it does come out so well, and it is not surprising on the other hand that what you get is actually nonsense, right? It's sort of random. So when you understand that, you're now in a position to say, okay, I mustn't expect magic from this thing. This thing is not intelligent. This thing is not going to revolutionize the world. It's certainly not going to compete with Putin's minions to change my opinion about anything. On the other hand, what could it do? I mean, this is much more than we could do before. Where is the limit? Given the constraints of this, where can we go from here? And I think that's the point of this panel, this topic, this discussion, and that I find fascinating. Thank you.
Yeah, let me, I think that's a really good example, Ed. And even though it was generated by the earlier generation platform or system, it's still, I think, illustrative of the kind of problems that one sees even when one scales up, though it gets smoother as one scales up, to be sure. The Guardian article that I showed earlier, in fact, was composed of several different sub-articles that had been generated by GPT-3, and editors decided how those sub-articles would fit together. So it wasn't entirely a top-to-bottom exercise done by GPT-3 alone. And I think that helps us understand a little bit of the strengths and the limitations in the following sense. This system, all these systems have very complex architectures that have been tuned over past experience and many new trials to convolve a great deal of information that is derived from in tokens, words, let's call them, that appear in small contexts like phrases and sentences, or maybe even paragraphs that are input to a system. And the result is a very, very large dimensional space on which various operations have happened through the training process and the calibration of the internal states of the system. In a way, you could regard this as an exercise in very, very deep and abstract latent semantic indexing into a corpus. You're learning a great deal about the lexical semantic relations among words that have appeared in various contexts. And that clearly goes beyond immediate phrases, because words actually do encode on their surface occasionally, in some languages explicitly, grammatical relations. And those grammatical relations reflect distance dependencies of one kind or another. So over huge amounts of data, the system does learn a great deal about how words fit together. And this makes it possible to achieve a high level of cohesion in small contexts like sentences or even paragraphs. Cohesion being the sensibility of the words as they butt up against one another. But longer discourses, well, even paragraphs, can run afoul of the problem of coherence, because for text to cohere, one really needs to have some underlying logic. There might be a goal that's being pursued. The sentences might be consistent in their way of adding up to that goal or making an argument. And these features become apparent only when we get into longer stretches of text. And in this area, something like the GPT 1, 2, and 3 systems will not perform especially well. They have no explicit knowledge of the world or explicit knowledge, especially of discourse. And there are many features of language that need to be mastered that require such explicit knowledge, even if it eventually becomes internalized. So I think we see at a stroke here both the strength, the remarkable ability of this very large space to capture very powerful representations of natural language, English in this case, but also the limitations. The strength of the system actually also is its weakness, because the power of lexical semantic relations is not sufficient to guide the production of discourse.
I guess I would say that, these technology has an impact on the general public, and, maybe they're scared, maybe they're excited, but there's also an impact on people within the field. And I think within the field, yes, the lexical semantics is an important part, but to me, the most important part is the flexibility, the fact that we can pre-train one model, and that model can go across so many different factors. It can be different languages, it can be different registers like informal text messages versus formal academic writing. And then we can have that one model do multiple tasks. So it can generate text as we've seen here. It can do summarization, it can do question answering, it can do machine translation, it can do grammaticality judgments, and all those things coming out of one model. Whereas in the past, every time we wanted to do something separate, we started with a distinct model. So I think that to me is more exciting than the fact that you can publish an article and claim that GPT is the author.
Absolutely. You hit on the two. I so much enjoy listening to you guys because you hit on exactly the sort of things that my students and I've been discussing. I've been wondering about two different where you can take this thing in two different ways. One is, as David was saying, how can you control this thing so that you don't give it a little English prompt and sort of let it run? You actually try to control its semantics. So you want to give it some kind of semantic level guidance in some sense that it understands, quote unquote, and that would make it speak more sensibly and speak language. And the other big direction is, how about arithmetic? How about other capabilities that are not overtly in text? What can you do there? So on topic number one, what some people have been doing in the communities, people in USC and other places, one of my students, you can say, well, I'm going to drive this thing by giving it sort of keywords, a little magic string of pearls to say, speak, make your sentence. I'll kick you off and make some sentences, but make sure you hit this sentence somewhere in your future, this word, and then make sure you hit this word, and you kind of lead it as a kind of a text plan in lexical space, just on words. You kind of sort of try to keep it straight. And that is the weakest kind of text plan you can imagine. Then you can try imagining putting a speech act and saying, not only must you hit this word, but now I want you to make a question. And then I want you to make a kind of rhetorical an answer or give an option or something. You can imagine decorating this little string of pearls into the future with more and more information, increasingly semantic or rhetorical, in such a way that the machine would actually try, if you could get it to understand what you're giving it, would actually be leadable. If you could take that to the extreme, you wouldn't treat the machine as just a big database of words or phrases, right? That it's just read and generalized a little bit. If you can convert that into a slightly more abstract level of representation, it's not quite clear exactly what the representation inside is, but it's based on words and word sets or parts of words and their similarity sets in context. If you can generalize that just a little bit and say, now, I want to tell you, now give me a number. Now give me something that's talking about a limitation of something, balancing something else. If you could start introducing some kind of simple semantic constructs into that internal knowledge base, the thing that it's read, have it somehow transform what it's read into your abstract language, then you may be able to run inferences to smooth out things and to avoid some of these inconsistencies. I mean, that's interesting, right? If you can make that happen. So that's one line of work that we've been doing. Just briefly on the other side, sorry to talk too long, I just want to briefly mention that in our stop is, what about arithmetic? I was wondering, can GPT-2 add? Can it add two numbers? Can it say 9 plus 3 is 12? So I looked on the web and I found a table in one of the papers from OpenAI where it says, yeah, up to two-digit numbers, up to way more than something 99 plus 1 or whatever, any combination of two-digit numbers, it can add pretty well, not perfectly, right? So I'm thinking, how does it do this? I mean, how does it work, right? So then at some point I discovered, I was fooling around on the web and I discovered there are lots and lots of tables that you can download on the web that give you the multiplication tables for kids, right? You stick it on the bathroom wall when the kids in the bath, they learn 8 times 7 is 56, right? So this thing has read that and it's got a little rudimentary lexicalized memory of certain kinds of multiplication and addition in a simple way. So it can do up to a certain level sums. It can do arithmetic, but it doesn't do arithmetic. It just regurgitates what it's read when you give it the input, right? So it cannot really add. It doesn't understand adding or division the way you and I do, but it can remember and it can regurgitate when it's seen it. And because it's seen so much, it looks intelligent. So that's an interesting thing. You wonder, can you somehow do something, some surgery on the inside there to make it able to take just that little bit of memory and do that magic that people do when they go from the memory into the reasoning pattern? What is that magic that you and I learned, right? When we learned how to divide or add or something more than 2 digits and so on. How do you do your surgery? So that's the other part of what we discovered, exploring. And if you can crack these two, even partially, imagine what you could do with something the size of GPT-3. Just imagine. Isn't that amazing? That would be so cool. That's what I think, to complement what Peter was saying, is the real excitement of this machine.
Yeah, I agree completely. I think this brings up some very interesting points and problems. One is just that if, in fact, we did have a system that had read everything and ingested it and could accurately repeat back to us what it had learned from reading everything, we wouldn't really care if it were more creative than that. That would solve a lot of problems right there and then. We'd be happy. But I think we're also all striving for some kind of artificial intelligence that more closely approximates the range of intelligence we see in the best examples of human intelligence. And you know, as we all know, we are neural net systems. We are just neural net systems embedded in certain kinds of bodies that interact in the world. And as we are learning through these neural net systems, we have lots and lots of different inputs in many different channels, not just language channels. And all of it gets somehow convolved inside our neural network. So language is enriched not just because of lexical semantics, but because of emotive semantics, because of textual semantics, because of features that derive from our own personal experience with words over time in various locations. And so I think that's the challenge for the kind of deep learning models that we're building. It's great if we can make an idiot savant that knows language, but it would be nice if we also had an idiot savant that knew everything about vision and knew everything about taste and knew everything about touch and knew everything about emotion and could somehow convolve these. If we could find a way to have each one of these models interact with the others. Now, there's some indication, of course, that our brain is actually organized that way, that there are certain parts of our brain that are more highly specialized for processing certain kinds of information. And yet it all gets interpreted. And one kind of information colors the other. So I think that's a real challenge for building the models. Not all of the information is as handy as the text on the web. Clearly, that has made it possible for us to move forward in developing rich models for natural language faster than we might in areas like emotion or touch. But I think those are definitely the kinds of challenges we face. And this is clearly a step in a direction that we're going to have to continue down.
I wonder, Peter, do you mind if I just give a little example? Is that okay? Now,
go ahead.
So one of the programs that I'm managing at DARPA now, we're looking at information on the web and trying to find alternative accounts of the same thing. So you say, you know, this person did that, and I say, no, this person did something else, whatever. And so when we look at the COVID problem, there are any number of statements about you should be vaccinated or you should not be vaccinated, or you should take this vaccine or not this vaccine, or you should wear this mask or not this mask, and all kinds of stuff. And these statements are not only, they don't exist only in text space, they also exist in images. Particularly, you have images where there's like a little red circle with a slash through saying do not, right? The negation thing. Now, image people in the image recognition community have never actually looked at this as a problem for them. What they typically do is they look at pictures and they say, oh, there's a cat, there's a tree, there's somebody running, there's a tennis game. And then they consider success when they can give a little English string that characterizes what's in that image, right? That's one part of the image recognition problem. And they use these internal representations called embeddings. So the challenge that we now face posed for the researchers is, I'm going to give you a bunch of these images with an overlay that has a communicative semantics of negation, right? You're going to see some text, and you're going to have to snapshot that text and OCR that text and whatever, so you get the text there. And then you're going to see the red line across or a big banner that says false or something. And you're going to have to understand the semantics, the communicative import of the semantics of that red line or that banner. And you've got to convolve them together so that when you come and the text people come in your same embedding space, you start putting these two media together, it's the same understanding of negation in there, right? It's not anymore the word NOT or the line of the thing, it's the understanding of negation as expressed in these two media in its own different ways. That's exactly what we're now starting to do here. And that's just one of several examples of bringing together the sort of communicative semantics of images and diagrams and charts and the communicative semantics of text into one central space, not just from French to English, but from English to picture, right? And you can imagine now taking that further, and exactly as you were saying, David, if we have the ability to stick a camera on the back of this GPT-3 machine, and it's watching what it's reading, it's watching when people speak, and it sees this one's face being unhappy, and sees this one shaking, and it sees whatever, the cold or whatever it is, imagine what it could then learn and start associating together inside. This is the path forward, I think. This is a path that one could explore, that we don't have any idea where it's going to end up. But given how far one can get when one has just lots and lots of text, there's a big world out there, there's lots of cameras, who knows where we'll end up.
Yeah, I wanted to just caution that just because these technologies have the word neural in them, doesn't mean that that's closely related to the types of neurons that are in our brain any more than, you know, we use the word fly for birds and for airplanes, but it doesn't mean they're doing the same thing. I also think we need to do a better job as a field of figuring out how to interact with these models, right? So we build these things and we can give them various tasks and measure how well they're doing on it. We can look at the output. But I think we really still don't have a very good understanding of what the limits are. And so I would like to have a way of breaking out these components, right? So we've talked about there's different languages, there's different modalities of text and images and videos and so on. And there's these various tasks we want to do. I would like each of those to be trained independently, you know, so we can say, well, now I'm going to be doing a question answering task, and it's a multiple choice question, and it's in English, and so on and so on. And I think up to now, all those things have kind of been conflated into one. When you give a prompt into one of these models, it has to figure out both what is the prompt talking about and also what is it expected to do as an answer. And I think we have more work to do before we can do that. And I think that's necessary to really understand what its capabilities and limitations are.
Yeah, understanding is what it's all about. You know, Peter, you mentioned something that is so, 3-4 years ago, I asked a student in trying to understand what the hell's going on inside a neural net, make me the smallest neural net that you can that would add 2 digits, the smallest one. So he came back after about 3 weeks and he said, here's a little machine and I've trained it. I took 1 million randomly generated 2-digit sums, 3 + 9, 0 + 4, 7 + 1. And I just trained it. And look, you can throw any 2 numbers, any 2 digits in, it'll give you the answer. Now you look inside at the little nodes, like 4 nodes or 5 nodes, and you try to figure out what on the activation levels of the numbers inside there, how is it doing addition? We could not figure it out. Maybe you can figure it out, but we could not figure out what's the logic, right? So then he said, now he did a clever thing. He said, now I'm going to give 2-digit numbers I mean, sorry, two, not just A plus B, but A plus B plus C. Again, single digit, but now three of them. And he retrained it. He had the same architecture, he retrained it, and the thing learned, it could do it. Then he says, now I'm going to do 4. 1 plus 7 plus 9 plus 3, 2 plus 2 plus 2 plus 4, etc. And he retrained it, and the thing worked. So every time this thing worked, and under no time could we figure out what was going on. And then came the kicker. He took the 3 training sets, the two sums, the 3 sums, and the 4 sums, and he scrambled them. Now this little machine is sitting there, and it doesn't know when you give it a digit, is this the last digit, or is there one more coming? Oh my God, maybe there's one more coming. So before, it had learned all possible pairs and all possible triples and all possible quads and gave you the answer. Now it doesn't know. And guess what it did? What was informationally advantageous to it was to create, to emerge, to create an accumulator node, a running total node. Now you look at this, now when you look at this thing, when you give it a random number, you know, from 2 to 3 to 4 possible sums, suddenly there's a node, one of the nodes has become designated as the running total. Now, when you give it a digit, and you look at that magical number, you'll see the representation of the sum of that. And you give another one, it's going to say, why did it do this? It just says, rather than remembering all the all the pairs and all the triples and all the quads, I'm just going to remember pairs, this magic little thing, plus one other, right? And I just have to remember a lot, but it's a lot of pairs. That was informationally advantageous to it for its training. So out of a very simple consideration, it emerged in an intelligent way, the running total node. That blew my socks off. I can tell you, that just blew my mind. I couldn't sleep that night. I thought, my God, do we have emergence here? Like, what is going on, right? It's very difficult to say what is the in principle limitations when you start throwing a lot of things together in an innovative way with curriculum learning. It's now being called this sort of, you know, you change the curriculum of how you teach the thing. So we're at the beginning of a lot of stuff. So we do have to, I think Peter is exactly right. We have to understand the individual component capabilities, and then we have to explore their juxtaposition and the way they play together to see what magic could happen then. And then we may be surprised. We should not be fearful, but we must be open and humble to look what's coming back at us and sort of really, really try to understand. I think that's why this is such a fascinating thing, because it's a big machine, right? And now you can do a lot of stuff with it.
Yeah, I think that's actually another good example of strengths and weaknesses, because it's pretty clear that the actual internal state that's created through the model is brittle in accordance with the kind of input it gets. Yeah. So you might have perfected a machine that knew all the 2 digits and all the 3 digit and all the 4 digit combinations, but it only knew those. And it was bollocksed when it was given something outside its previously exposed set of examples. And yet, when you trained it in a slightly different way, it seemed to have internalized the generalization. And the generalization had a lot more power. So either we have to be very, very clever as trainers, or we have to find out what's actually going on at some level of representation in the networks and then play to that strength. Now, I think GPT-3 probably has a lot of both. It probably has a lot of surprise generalizations because of the high dimensionality of its abstractions. It's seen so many different combinations that it's found relationships, ineffably perhaps, that we cannot even imagine, that give it power in specific task circumstances. But it's clear that we could train better. And in this area, I think there are some areas where GPT-3 might do better in natural language if it had input tokens that reflected more naturally the actual natural language structures that it was supposed to be mastering. For example, I don't believe that the input tokens are necessarily correspond to morphemes or any of the meaningful substructures that language offers. Some, I believe, are just large words that are broken up into letter engrams of various kinds. Some are whole words. Some might even be phrases. Those details are not apparent to me. But I think we might see some interesting possibilities if we trained it on phonological representations and morphological representations and even some syntactic annotations. It would be very interesting to see if we accidentally or on purpose achieve some other level of generalization that will surprise us.
I mean, if you can imagine taking a sentence and for each word adding 6 or 8 little things underneath it, little decorations, right? As you said, the phonology, the fact that this is a Latin or a Romance type word, the fact that this word has another sense that is derived from it that is a modern technology sense, and this one doesn't, whatever, anything you can make up, right? This has 4 T's in it, and that has 1 T in it, or no T's in it. Whatever you can put in, this machine in its blind eagerness will learn any kind of generalization that it can. And in your training of it, if you can make better kinds of training than the training that GPT-3 and similar things are trained to just find a similar word in context, right, as Peter was saying, but you can actually train it to do more interesting kinds of things. It will blindly collect and say, you know, when I have this little feature here and this little feature and this little feature and stuff like this, these are the things that help me, that give me positive points in my training, that help me give the answer that you want to get from me, right? So at the moment, the only training regime we have for these large language models is, here's a sentence, as Peter said, I blank out a word, give me back a word that fits into that context. So it's just got to find words or subwords that have the right kind of combinatory flavor with all the words left and right, or all the subwords or sort of abstractions of them left and right in such a way that the overall pattern makes sense. That is like the most simple and language-oriented training regime you can imagine, right? That's just saying, give me back the same thing and I'm blanking out one word. If you start throwing in a whole bunch of numbers and stuff and saying, now give me back the sum, give me back the factors, give me back, you know, give me back the Roman numerals. I don't know what. There is so many different ways you can imagine creating a training regime easily with training data, gold standard data easily, that you can explore for a long time. One thing that's actually holding us back at CMU is the size of the machine, right? We don't have the machines to do this. So Peter, I am so envious of Peter because he's sitting there with 75 billion power machines there, and I'm sitting with 4, right? And so I wish we had the sort of power to do these kinds of explorations at the size that say Peter does. And of course, all our students run off every time they can, as soon as they can, and they go and visit Google and Facebook and everywhere for the summer. And they come back with stars in their eyes and they just want to do stuff. And I'm saying, I'm sorry, what can we do? So I think that we should, around something like GPT-3, create a consortium, a better consortium between universities and a kind of a university industry place where we can jointly explore and educate and do things much more without this barrier between us, you know, the completely permeable, that one can explore this stuff much more easily. I see Peter nodding. I'm happy to see that because this is kind of a wish or a dream that would be nice.
So Ed, I remember, I guess a decade ago now, going to UPenn to give a talk, and our colleague Fernando Pereira stood up at the end and he said, I feel like we're all particle physicists and you guys are the only ones with a super collider.
I remember that. Yes, right. I remember that. Yes.
And as you know, he soon after ended up at Google. But I think we're in a good place now where these large companies that are at the forefront of this research and are also cloud providers, I think they have an incentive to want to rent out these capabilities to companies and to want to give it away free to universities so that the students become more familiar with it and be able to do more with it. I think, you know, that's been delayed a little bit just because we're not quite ready yet. We don't really know, you know, companies understand how to rent out a database or how to rent out compute in general, but they don't quite understand how to make a service out of a natural language model. But I think that'll be coming soon, and you'll see all the cloud providers happy to have more people on their platform and sharing that and giving away credits for free to universities.
Yeah, and jointly educating and exploring, right? I mean, bless you guys for especially bless Google to Norvig for distributing BERT, right?
Yeah.
Because you guys did. And before BERT came out, in those 3 months before it was publicly announced, I was sitting there doing my sums and saying, I can buy as many machines as I can afford, and it's going to take me 3 years to build something that even approximates that size, and then just keep all those machines building all of, and then out comes this announcement, you can have BERT. Wow, can you imagine how nice that is? So having something like GPT-3 and having the machinery and the underlying substrate of GPT-3 so that one could retrain it with new kinds of reward functions, for instance, or that one could plug a camera on and say, yeah, I'm going to pull out all the sentences about tennis games, and I'm going to pull out all the movies about tennis games. I'm going to stick 6 cameras on them. I'm going to try to put this stuff together under certain kinds of reward functions, or the communicative semantics of images or tables or charts or graphs. There's just no end to it, right? But we need a machine. Yeah.
I hope we can get there. I mean, even Google doesn't quite have enough computers yet to process all the YouTube videos.
A depressing thought.
Yeah. But
I don't want to,
so guys, we're coming to the end of our session, and we'd like to take time for some questions. Before we do that, I'm thinking maybe we should look at the takeaway slides, Jason. I anticipated what we might be talking about GPT-3 like, and I projected out the answers to the question, what did we say? And so I wrote some slides, and takeaway number 1 is that GPT-3 is a remarkable and powerful system. It's clearly capable of human-like performance in some areas of natural language processing, but we should beware ELIZA effects, resist reading more intelligence into the behavior than actually exists. It's still a black box. It's not possible to comprehend the architecture and data structures or to draw analogies from them to anything in nature. It's really not possible to explain the behavior we see. Next one. There are strengths, and GPT-3 strengths reflect its rich lexical semantic abstractions. This makes local text cohesion possible, even supports some extended text production, and that clearly has implications for applications. The high dimensional lexical semantic relations provide a basis for many natural language processing tasks, especially at the level of sentences and paragraphs. So there we really have demonstrated, I think, in this system, something that will perform at a level that most humans would find quite acceptable. Takeaway 3, but there are weaknesses, and these weaknesses result from the inability for the system itself to engage in planning or user modeling, in addition to the paucity of conversational, pragmatic, and paralinguistic information in its training corpus. This can lead to a failure in coherence in extended text production. Coherence derives from the logical connections between the ideas, and there's nothing in GPT-3 that guarantees that that will happen. So language-mediated human interaction requires functionality that goes beyond rich language understanding. It includes practical world knowledge, nonverbal components of communication, planning, intentionality, and critically modeling the interlocutor. This is all beyond anything that's part of the GPT-3 suite. Finally, the last takeaway, evaluations are important. They're the only way we really understand what we can say about system performance. But the evaluations that are used today, including the huge battery of evaluations that was used for the GPT work, are incomplete. They don't measure a full range of behavior required for human discourse. And while we're improving our systems, I think one of our challenges will be also to improve how we evaluate them. That is still far from a solved problem.